Okay, there's no problem.
Was my connection.
Can you see my screen?
Yeah, we can see it. Thank you.
The type of is source tag selection for time series via performance prediction. My name is Jesus Garcia Ramirez, and the co-authors of this work are Eduardo Morales and Hugo Yair Escalante. And this is part of my PhD thesis. The content of my presentation will be the next. I will start with a brief introduction. Then I will show you some related work. Next, I'm going to present the method that we used for the performance prediction. Then I will show the experimental results, and finally the conclusions and further work. I will start with the introduction. Deep learning has shown a good performance in different tasks. Here I show you three of that task. First, AlexNet, that won the ImageNet contest in 2012. They proposed to use a deep model to classify 1,000 of classes. Other one is DeepQ networks that outperform human level in different Atari games using frames as input of a convolutional neural network. And Alpha Stars that win experts in StarCraft, that is a difficult strategic game. Nevertheless, deep learning has important limitations. Some of them, and the most important for me, are the long training times, even with specialized hardware like TPU or GPU, and the large number of instances that are needed to achieve an acceptable performance. This is because deep model has millions of parameters. For instance, AlexNet contains 60 million parameters. Another example is DeepQ networks that has 4 million parameters. An alternative to reduce this limitation is transfer learning. In transfer learning, there are one or more source tasks that with enough instances to obtain a model with an acceptable performance, and a target task with few instances that are not sufficient to obtain acceptable performance. Here, the pre-trained model in the source task is used to initialize the training of the target task. Then this model is fine-tuned in the target task to obtain a better performance than the training from scratch. The main limitation of transfer learning is negative transfer that appears when the training from scratch obtain better performance than the transfer learning strategy. Also, neutral transfer is obtained when the performance with transfer learning and the training from scratch are the same. Then Yang et al. Discussed three important questions to take into account when we develop transfer learning methods. First, when to transfer. This question is related to the selection of a set of source tasks, one that will obtain a good performance in the target task. Then what to transfer, that determines the part of the knowledge that will be transferred to a new task. And finally, how to transfer, that refers to the method used to transfer the elements to a new task. In this work, we approach a little of the three questions, but we focus on the first one, that is when to transfer. That for this, we propose to predict the performance of a pre-trained model in the target task using a regression model. And we select the pre-trained model that predict best performance. We use for our experiment the time series domain. In this work, we approach the source task selection in this domain. And a time series is another set of values or real values in the form of the second bullet. We propose a method for selecting a source task using as features the entropies of the hidden units. And our proposed method uses a regression model to predict the performance of a pre-trained convolutional neural network And we rank the pre-trained models according their predicted performance. And finally, we select the most relevant. Now I will show you some of the related work. We compare our method with two other approaches, and I will show you the first one. The approach proposed by FAWAS proposed to use a reduction of their data averaging the data in each class and obtaining only one prototype for each class. Then they find the most closer prototypes using a dynamic time warping coefficient to obtain the distance between classes. And they select the source task that is more closer to each one. Then Micheles et al. Proposed to use the output of a hidden layer in a pre-trained model, and then they use the mean silhouette coefficient to determine the separation between classes of the target task. They rank their pre-trained model with this mean silhouette coefficient, and they select the best one. Here I show you what each method need. FAWAS et al. Need the source data and the classes to predict the pre-trained model. Micheles et al. Need the pre-trained model and the classes. And the proposed method in this paper only need the pre-trained model, so it can be applied in other domains like deep reinforcement learning or semi-supervised learning. Now I will show you the proposed method for the performance prediction. Here you can see the proposed method. First, we have as input a sample of the target task and a set of pre-trained models in different source tasks. Then we obtain the output of the hidden layers in each one of the hidden layers, and we find the feature map in the convolutional layers and the output of the fully connected one. Then we discretize the features maps and also the output in a fully connected layer, and we find the entropies of each unit and each convolutional kernel. Then we train a regression model to predict the performance of this pre-trained model in the new task, and we select the pre-trained model that predicts better performance. And now I will show you the experimental results of our method. For our experiment, we use a UCR archive that contains 85 datasets of multimodal time series. Some examples of them are the following. The B2Fly datasets contain image data, the 4K contains source data, and Cricket J contain motion data. We use to build a regression model those data that instances in their training data. Now to validate a proposed method with next metrics, first top one precision, that is the where the optimal pre-trained model is obtained in the first position. The top one mean, that is the mean position where the optimal pre-trained model is obtained. The maximal useful, that is the maximum position where a useful model is obtained, and mean useful, that is the mean position where a useful model is obtained. And a useful model is or a positive transfer or neutral transfer. And finally, the precisions in the first, second, and third position. We select random forest as the regression model because this algorithm obtains good performance in regression tasks. And we test different hyperparameters to obtain the best one. And after that, we select 18 trees to build a forest, and mean square error as quality measure. This best performance in the different metrics that I showed you before. Also, we compare our method with the state of the art. Our method outperformed the Mercedes approach in all the different tasks, but compared with the FOWAS method, we only perform in the top one precision, the top one mean, and the useful maximum position. Here I'm going to show you the conclusions and future work. Here, our main contribution is a method for selecting a useful protein model to train a new task using a meta-learning formulation in a time series domain. To predict the performance, we use a regression model, and we run the protein model to select a useful source task in order to avoid or to reduce the negative transfer. Our method selects the optimal model in more datasets than state-of-the-art method. And also we guarantee to obtain a useful model in better position than other proposed methods in time series domain, specifically in UCR archive dataset. Differently to the state-of-the-art, our method doesn't need the classes, and consequently it could be applied in other domains such as semi-supervised learning or deep reinforcement layer. The main limitation of our work is that it's an example of the transfer learning performance in the dataset. But to alleviate this, we use the datasets with less instances in their dataset. And for future work, we will test other set of features or complement those that we propose in order to obtain better performance in the predicted pretended model. So that's all for me, and we have the source, the code in the next GitHub repository.
Yeah, I think you finished, yes?